Hello, I'd like to welcome you to our Physics 211 Group Project Number 1, presented by Justice Peyton, Jacob Reierson, and Ceiba Cummings. Throughout this project, our group utilized concepts from our Physics 211 course, which included kinematic principles applied in a 2D setting, and the use of integration to find velocity and acceleration. For our group project, we are given the task to design a helicopter for the next Mars rover. For organizational purposes, we have decided to present our problem-solving steps in the format for writing the solution to a real-world context problem. We are given that the helicopter lands along a horizontal distance d. The values of alpha and beta are constants, which we can disregard in our problem-solving steps for simplicity. We made the following assumptions as seen on the screen. Air resistance and density is negligible. The helicopter is constantly moving forward, and since displacement is being solved for, elevation will be irrelevant. For this process, we have established that the units for the constants alpha and beta are unknown, and our main goal is finding the amount of time spent in the air and the location of where the helicopter lands.
In this slide, we're going to be solving for and making sense of alpha, and we can do that by looking at the vertical component of the main equation that we are given and writing out the units of that. Since we know that lowercase t is a time and the uppercase t is also a time, and we know that because we are told that negative t is the initial time, we can cancel everything out to find that alpha has to be a unit of distance over a unit of time squared. Using the same process that we did for alpha, we can solve and make sense of beta by writing out the units of each of the pieces inside of the x-based or horizontal component. In doing this, we can see that t is a unit of time, both the uppercase and lowercase, using the same claims as we just did before, meaning that beta is also a constant of acceleration and has to be distance over time squared.
We split the equations up into different components, where x hat is the x component of the vector and y hat is the y component of the vector. Through integration of this vector, we can find the velocity and position of the vertical and horizontal components. We take the integral of acceleration to get velocity function. We solved for the initial condition by setting the velocity function equal to 0 because the helicopter starts at rest, then plugged in the initial time of negative t, which gives us the initial conditions. It is important to add on the initial conditions after solving the interval. The position function can be solved for by taking the integral of velocity. We assume the helicopter starts in the ground at an origin of 0, 0, and the initial positions will be 0. Since displacement is being solved for, we will also add in the initial conditions. The position function can be used to solve for the displacement of the helicopter after the time and air is found.
On this slide, we'll be solving for and making sense of the constant t. We're told within the scenario's description that the helicopter takes off at time negative t, which means that it's a unit of time. Notice that in the horizontal vertical velocity equations that plugging in negative t, which is the initial time, into the equations gives us a value of 0. This makes sense because the horizontal vertical velocity should be 0 because the helicopter starts at rest. It's worth noting that since the input value for velocity is always squared, the value that it will give afterwards is always positive. This actually shows us that potentially the final time could be t, or at least another point when the helicopter is not moving. To prove that t is the final time, we can plug negative t into the horizontal distance equation and isolate it. Since when we isolate it and solve for t, this becomes a square root. That means the value that can be returned can be either positive or negative, meaning that the final time is just positive t. Again, we are also assuming the helicopter does not stop until it reaches its final point, meaning that positive t is going to be the final time. We're asked two main questions. Where does the helicopter land and how much time does the helicopter spend in the air? For the first question, we can plug in the final and initial times into the horizontal position equation and find the displacement from the initial position and the final position to see how far it landed from its initial position. We can do the same process for the helicopter's vertical position, except with the vertical equations. And for how much time the helicopter spends in the air, we can use the equation, which is shown there, to find the time spent in the air. On the slide, we'll be solving for where the helicopter lands horizontally. And to find that, we can need to find the distance where the helicopter lands from its initial position, which means we need to find the change in x, which is depicted here as dx. This can be done by getting the initial horizontal position and subtracting it from the final horizontal position, which we can get that down there at the very bottom of this slide. This makes sense because beta is a constant of acceleration and it is being multiplied by time squared, which means that this is overall going to just be a unit of distance. Similarly to what we did for solving for horizontal distance, we can do the same process for vertical distance. We can find the initial vertical position and subtract it from the final vertical position. This will give us the very bottom equation, the bottom left one, dy, which is just going to be change in x. And that answer that we initially have is correct. It gives us the time squared multiplied by distance over time squared, which gives us just the unit of distance. However, since we know what time is, we can plug what we know into it, which gives us alpha over beta, which is just distance over time squared, divided by distance over time squared, which gives us a value of nothing. But it is multiplied by dx, which is a unit of distance, which means that this answer is still in a unit of distance. A few slides ago, we found this equation, t equals the square root of 3 dx divided by 2 beta. To find the total time in the air, we can use this equation and double it since it is only going to give us a negative or positive value and we want an absolute value. Another way to find how much time the helicopter spent in the air is by finding the critical points of the vertical velocity. This gives us the values negative t and t. We can just double the positive value of t because we want an absolute value.
The first thing I want you to notice when looking at these graphs is that the specific numbers don't matter, rather the trends are what we would care about. Another noteworthy aspect is that the dashed lines represent negative capital T, start of flight on the left, and positive capital T, end of time of the flight on the right. So these aspects will be important to remember in the next few slides. But now let's dive into these specific graphs. Let's start with the graph on the left, which is the graph of acceleration in the x component. We can determine some interesting knowledge about the helicopter's motion. For example, when lowercase t equals 0, the helicopter stops speeding up and begins to slow down. Now looking at the graph on the right, which represents acceleration in the y component, we see that if we increase alpha, the magnitude of acceleration in the y direction increases. Additionally, the graph shows us that acceleration is the largest at negative capital T and lowest at positive capital T. And finally, in between these 2 points, the acceleration changes direction 3 times. Now these graphs represent the velocity of the helicopter, both in the x direction and y direction with respect to time. Looking at both graphs, we see that velocity is 0 at negative capital T and positive capital T, which means that at these points, the helicopter is at rest. The graph on the left, which shows velocity in the horizontal direction, is pretty straightforward. It starts at rest and then has a positive velocity until it lands. As for the graph on the right, the graph shows that the helicopter starts at rest, then has a positive velocity until around halfway through the flight. Here it has a constant velocity of 0, meaning that the helicopter holds a constant elevation over that time interval until shortly after when it begins to have a positive velocity again, and then finally returns to 0 at capital T. Both of these graphs show that the displacement in the x and y direction are positive. It is also interesting to note that the displacement is proportional to the respective constants, horizontal with alpha and vertical with beta. The graph on the left shows the position in the x direction versus time, which demonstrates that the helicopter is always moving forward relative to our coordinate system. As for the position in the y direction, we see that the height originally increases and then begins to remain constant and increases one more time before it lands. This is the final graph I will show you, and it has a few purposes. First, it represents the helicopter's motion in the horizontal and vertical components together, rather than splitting them up and showing them with regards to time. Additionally, this graph proves that the initial position is the opposite value of final position. This can also be thought of as we start at negative capital T and end at positive capital T. There are many ways to make sense of this problem. Firstly, we can look at the fact that the helicopter starts at rest at capital negative T, and since we end at capital T, we would also hope to land at rest at this point. We know this is true because the velocity equation only has positive exponents, meaning no matter the value of t, it will be positive, and since t and negative t are equal but opposite, they will return a velocity of 0. A main point I want to look at in this problem is that we do not land at the same height to which we start, which is known because we started at a negative y value and end in a positive y value. A real-world example that explains this is if we started below the surface level in a crater and flew up to land on a cliff. As well, the graph above makes sense because it shows that we are always moving positively in the x direction, and then we travel upwards for a while before staying at a constant elevation and finally elevating one more time before our velocity reaches 0 again and we land. When checking units, we left all work in terms of their bases rather than assigning arbitrary units. For example, for distance, we use d rather than m for meters. The work here shows that the units cancel out as expected for the position function. You can pause it here if you would like to look over them. This slide shows the units used in our time equation. They also canceled out according to t equals t, which was expected. Again, pause here if you would like to see the work I did to obtain this. One way to verify that our answer is sensible is by checking special cases. For example, we can plug alpha in as 0 to see what the graph will do. In this case, the vertical acceleration would be non-existent, meaning the helicopter would move only horizontally and have no vertical displacement. An example of this taking place could be a helicopter taking off from a ledge and flying in a straight line at a constant elevation. Another spatial case we can look at is doing the opposite, by making alpha a very large number near infinity. In this case, the vertical acceleration would be extremely large, causing the helicopter to travel upwards quickly, but maintain the same horizontal displacement. We can also look at special cases concerning beta. These cases will regard to the horizontal component in time, but I don't have time to talk about them, so their descriptions are attached on this slide. The first problem I wanted to mention was the Mario Kart problem from the lecture. The two problems are very similar. In general, it helped us understand the concepts of a physics problem with a real-world setting and taught us to convert variables and equations into visual motion using integration and kinematic equations. Some of the other similarities and differences are listed on this slide.
The second comparison problem is the ball and cliff question from homework 1. Both problems are set in the real-world context in 2 dimensions and require the understandings of kinematic principles. The two differed in the methods for solving and the amount of given and unknown information provided from the question.
As a final note, here is our team's reflection on the teamwork and also the sense making. Unit assignment allows us to size our results. Unit sense making allows us to find what variables are and check our own custom-made equations. And graph sense making allows us to visualize the scenario that we have. In regards to teamwork, the team bonded over the struggle and stress during the project, and we also relied on one another by dividing the work equally. And overall, it was a very fun experience to work with everyone.